So hello, everybody. We are back on track with the webinar sessions. We had a little break. We promised you that we will be back in February, but due to some pretty intense networking activities, we had to reschedule some of the webinars. I promise you that this one is going, that the webinar that's supposed to be in February is going to be focused on genomics and microbiome, but we needed to switch a little bit. So we will get back to that topic, but currently we have with us a colleague, Nikolina Pleić. She's coming from School of Medicine, University of Split in Croatia, very nice town near the seaside. I don't know how she managed to get all this amazing work done being based around the sea, and why she's not a marine biologist, but maybe she will share details of that story with us at some point. She's currently, if I'm not mistaken, also leading the InnoThyroGen project. Her PhD was on use of Mendelian randomization, and she's currently doing a lot of these genomic cool studies related to thyroid disease. And one of the things that I really kind of struck my eyes is to see so many European projects on this slide. So CardioSCOPE coming from my side, and AtheroNET coming from our side is Inflammomix, new cost action, and InnoThyroGen project coming from Nina's side. So I think this is European Union and Commission would be very, very pleased to see this type of collaboration. So without further ado, please enlighten us with all fascinating things behind the Mendelian randomization. You have around 40 minutes to present, and then we will come back to ask some questions and to open the discussion. Thank you so much.
Wonderful. Thank you, Miron, for this very nice introduction. There is not much to say more about me. As you said, my PhD is in biomedicine, and it was on the topic of Mendelian randomization. I have a master's degree in mathematical statistics, and I'm also a lecturer in statistics. So here, my main idea was to present the, let's say, the math behind the Mendelian randomization. How does it work in practice? I promise it's not going to be too complicated. I try to keep everything, accessible to a wider audience. But as from my side of view and my point of view, I always like to understand the basics of the methods that I'm using. So I'm hoping that this introduction to Mendelian randomization and the background behind the code that we are running is going to be useful for all of you. As you said before, this webinar is held within the framework of all of these Horizon Europe and Cost Actions, CardioSCOPE, AtheroNET, InnoThyroGen, and Inflammomix. And I am the primary coordinator of InnoThyroGen project, where we are applying Mendelian randomization to specific thyroid dysfunction diagnosis and parameters. So without further ado, I'll start with the presentation. This is a nice cartoon or an image that I use frequently when I present my papers on Mendelian randomization at various conferences. We can see here today's random medical news from the New England Journal of Panic-Inducing Gabblejock. I can't even read this, but you can see that on the left side we can read that today coffee can cause depression in twins. So coffee can cause depression in twins. It's today's news, and this is not something that we are not used to. You can see these kinds of news titles frequently. So one day, I don't know, eggs are good for cholesterol. The other day, eggs are not good for cholesterol. The problem is that there are various epidemiological studies that are studying these associations or correlations, and then these studies, or a subset of them, get caught by the mainstream media, and the mainstream media usually presents it in this kind of way. So the results is that the general public is pretty confused about what's the true effect of things. What are the changes that they should introduce into their lifestyle if they want to improve some kind of outcomes, be it health outcomes or lifestyle outcomes, or in general, the quality of their life. So this is where we have to, especially as statisticians, step in and try to decipher between correlation and causation. So as you know, correlation does not imply causation. We'll get to that also. But these conflicting associations are everywhere, not just in medical research. And with Mendelian randomization and with causal modeling, we are trying to go beyond the epidemiological statistical associations and go into causal modeling as much as we can using the data that we have. So here we have another example of a spurious correlation. You can see here that mozzarella cheese consumption correlates with bachelor's degrees awarded in engineering. And the graph is very clear about this. This is taken from a website of InnoThyroGen, and this is a spurious correlation number 8507. You can go to this website and you can explore all of the spurious correlations that are present in this data set. And here we can see that the Pearson's correlation coefficient is equal to 0.974, which is basically a very strong positive linear correlation. And you can also see that the coefficient of determination is also very high, and it was statistically significant at the significance level of 1%. So from this graph, the question is, can we conclude that mozzarella consumption causes engineering degrees? I guess we would all disagree with the causality direction in this case, but it's an established correlation with a very high correlation coefficient. And here is the question of the direction of causality and also the nature of this relationship. That's something that we want to dive deeper into with Mendelian randomization, and we want to represent it mathematically so that we can see what is the causal effect behind this, if there is one. So when we talk about correlation and causation, we are often interested in epidemiology whether an exposure has a causal effect on an outcome. So for every exposure that we are investigating for some kind of disease outcome or mortality or so on. So this is not the same as asking whether the exposure is merely associated or correlated with the outcome. It's asking something more complex, and that because of that, the models are a little bit more complex than it is with the correlation that can be measured with the Pearson correlation coefficient or some kind of other, let's say, Spearman correlation coefficients. So usually standard observational analysis, they identify associations, be it a correlation, positive, negative, be it a linear correlation that's measured with Pearson's coefficient, or be it a monotonic correlation that's measured with Spearman's coefficient. But these associations alone do not tell us what would happen if we intervened on the exposure. So in our previous example, this association does not tell us what will happen with the number of bachelor's degrees in engineering if we change the amount of mozzarella cheese consumption. That's just something that we cannot infer from this association alone. So this is where the famous saying comes in: correlation does not imply causation, and that's something that we have to keep in mind always when we are dealing with these kinds of epidemiological analysis. So why can it be misleading? What's the problem with the simple correlation? So a correlation between two variables, for example, X and Y, or in our previous example, mozzarella consumption and the number of bachelor degrees in engineering, it can arise because the exposure actually causes the outcome, or the outcome causes the exposure. In that case, we have reverse causation, or both of them, both our X variable and our Y variable are influenced by a third variable, and this is called confounding. And I think we are from the field of epidemiology, we are we know about confounding, and that's something that we try to control whenever we can. So the point of this slide is that observed association alone cannot distinguish between these three possibilities. It's just not something that can be done. But what's the motivation behind Mendelian randomization? It's that we are interested in modifiable causes of disease. So I'm interested at modifiable exposures that can cause my outcome of interest, be it a disease or mortality or the level of some kind of blood parameter, whatever. So what are the methods for and what are the limitations of making causal inference from our observational data? So here again, we have a visual representation of what we were talking in the previous slides. So we have the, let's say, the scatter plot. The blue dots are representing the data points with the values for both the variable x on the x-axis and variable y on the y-axis. And we can see visually that these points are following, let's say, some kind of imaginary line. And this line is added to the graph as the red line that you can see. So it has a positive slope, and we can imagine a regression model with a positive coefficient explaining this kind of relationship, or equivalently positive Pearson's coefficient for this linear correlation. But the question here is, what can give rise to this slope? So it can be either that x is causing y, or that y is causing x. In that case, we have reverse causation, or that a common confounder is influencing x and y, or in other words, it's influencing x and y to appear correlated to us, even though there is no direct causal network or causal connection between x and y. And that's something that can be applied in any field of science, but how can we use genetics or genetic data to improve this identification, to try to answer the question, what can give rise to this slope, using the data that we may obtain from publicly available data set, or that maybe we have at hand in our own databases. So as you all may know, our genome is 3.2 billion nucleotides long sequence. So base pairs or DNA letters are comprising this sequence. And usually when we perform analysis, we are coding these letters into numbers. And wherever you are coding something into numbers, then a group of mathematicians just joins the biologists and medical doctors, and we take over the analysis. That's just a joke. But when we switch to numbers, and we try to code all of these nucleotides with different kind of coding, it gives us a new possibility. It opens up a new space of different mathematical models that we can use. And that's something that we are actually using in Mendelian randomization, as well as in GWAS analysis, or genome-wide association analysis. One great point about the human genome is that it remains constant throughout the individual's lifetime, with some notable exceptions being cancer. But it's an ideal starting point for scientific research, because once you measure it, so you only have to measure it once. It doesn't change, and you can have the data for all of your participants as a stable data set without any changes. And that's a really great property, and it's very rare in biology that we have something that that does not change throughout the individual lifetime. And so, since we are working with the genome, we can use the Mendel's law of segregation and random assortment, which say that the genetic sequence is fixed from conception and therefore free from reverse causation. So the environmental exposures cannot influence the genetic sequence, again, with the notable exceptions of cancer. The second one says that the direction of causality is always from the genetic variant to trait. So not from trait to the genetic variant. This is also a great property. And also genotypes can therefore proxy for some modifiable risk factors, and there should be no confounding of genotype by behavioral, socioeconomic, or physiological factors. And because of all these three properties, the genetic variants are potentially very good instrumental variables, or in short, IVs. So using genetic variants as IVs is a special case of IV analysis, or instrumental variable analysis, which is known as Mendelian randomization. So instrumental variables analysis was something that was concepted in the field of econometry, but it was very cleverly transferred into statistical genetics by the group of Professor George Davis Smith at the University of Bristol, and they applied the same methodology using our genetic data to try to infer causal connections between different exposures and outcomes in our biomedical field. So you can also look up the reference at the end of the slide, which is the seminal paper that introduced the method of Mendelian randomization, and it was back in 2003. And so here we have a parallel graph of both a randomized control trial and Mendelian randomization. This is to say that Mendelian randomization is, in a way, mimicking an actual randomized control trial. So it's basically a natural analog of randomized control trial. We all know that randomized control trials are the gold standard for inferring the effects of different exposures on different outcomes, but they are pretty much usually very expensive. Sometimes they are not feasible, and sometimes also they are not ethical. So in cases when they are not feasible or they are not ethical, or that we simply don't have enough funds for performing them, we can, in some cases, refer to Mendelian randomization. So in a randomized control trial on the left, we usually start with the randomization method, which would, in this case, be equivalent to the random segregation of alleles that happens during the conception, so during the formation of the human genome. And then after the randomization method, we will have two groups in an RCT. So we will have the exposed group that is receiving intervention, and we will also have the control group that is receiving no intervention or it's receiving a placebo. And also parallelly in Mendelian randomization, we will have the exposed group of people who will have functional or affect alleles for some kind of disease, or we will have control group, which will have null alleles or reference alleles for some kind of defined outcome. And between these two groups, the fundamental assumption is that the confounders are equal between the groups. In a randomized control trial, we are trying to design this so that the confounders and all the environmental effects are the same between the two groups of exposed and control people. And in Mendelian randomization, the confounders are equal between the groups just by the nature of the randomization method here, and that's the random segregation of alleles. And then when that's done, we can compare outcomes between the groups and establish some kind of effects that would be free from confounders, since we have controlled for them either by design or by the nature of Mendelian randomization. So going beyond this, we go to the assumptions of Mendelian randomization. So it's a method that will not work if some or these three assumptions are not satisfied. So the first one is the assumption of relevance. We want the instrument Z to reliably predict the risk factor of interest. So here the instrument Z represents the genetic variants that are associated with our exposure. So X is representing the exposure and Y is presenting the outcome. So the exposure can be some kind of modifiable risk factor, and the outcome can be disease or mortality or anything else. And Z is basically our genome, or the single nucleotide polymorphisms for our genome. So we want this Z to be strongly associated with X. That means that the genetic variants in the genome have to be strongly associated with our exposure. Secondly, we also have the assumption of exchangeability, where it says that the instrument Z has to be independent of all confounders U. So we can see that here we have this line as crossed. So the genetic variants have to be independent of these confounders, and they also have to be independent of the outcome Y. And that leads us to the third assumption, that's the exclusion restriction. And it says that the instrument Z has to affect the outcome Y exclusively through its effect on X. And that's this line here. And it cannot have a separate effect to our outcome that it's not including or being mediated by Rx. So these three assumptions are the key for Mendelian randomization results to be reliable or for the method to work. The problem with them is that we can only test the first one. So we can only test the relevance assumption just by using the data from the genome-wide association studies that are relating the genome with our exposure of interest. But there is no way to test for the exchangeability or the exclusion restriction assumption. And this is something that kind of complicates the performance of Mendelian randomization analysis, but there are some ways that we can try to do the analysis as much as we can in a way that it should be valid, and we'll come to that later on. So what's the math behind the Mendelian randomization analysis? I know that some people maybe will try to perform it just by following some kind of basic tutorials and running the code in either in R or in Linux, but I think it's very important that we know what's in the background of the method, because otherwise you would be reporting some kind of effect and you would not have the understanding of what that effect is measuring and how we obtain that effect. So in Mendelian randomization, we have a parameter of interest, that's the beta xy, and that's the causal effect of our exposure on our outcome that we are trying to model with our Mendelian randomization analysis. So here the X represents the exposure, so some kind of modifiable risk factor, and the Y represents our outcome, some kind of disease, let's say. And this is the direction that we are interested in, and this is the causal effect that we are trying to model and that we are trying to estimate. There's a complication. So the association between X and Y is confounded by U. U is the confounder or set of confounders that can be confounding this relationship. So as a solution, we use the genotype as an instrument, and now the correlation between G and Y will provide evidence on this estimate beta XY. It sounds pretty crazy, but I'll show you how we will obtain this result that the correlation between G and Y will provide us evidence on beta XY. And here we also have the explanation. So beta GX will be the effect of the genome on our exposure. Beta XY is the causal effect of X on Y. Beta UX will be the effect of the confounder U on X or the exposure, and beta UY will be the effect of the confounder U on our outcome Y. And we also have the untestable assumptions that we mentioned on the previous slide, that there is no association between G and the confounder U. If we go further on, we will regress our exposure X on the genome G, and we can estimate the conditional expectation of X on G, and it will be given as an equation that you can see here. So it will include this coefficient beta GX, and we will basically be regressing our exposure on the genome. Try to do that also regressing our outcome on the genome, and we assume that X mediates this effect, then we will have the conditional expectation in this way. So if the assumption is that X is mediating the Y regressed on G, then we have to include X in this equation, and then the coefficient here will be a product of beta XY and beta GX. And alternatively, if we directly regress Y, our outcome on the genome G, then we can note it like this. And then we will have just the coefficient beta GY that will be represented right over here. But since the assumption is that there is no direct effect of G, the genotype on our outcome Y, then this coefficient beta GY has to be equal to the mediated term. So to the product of beta XY times beta GX. So from this equation, we can now estimate our causal effect beta XY just by dividing with this one, and we get the final, let's say, ratio for our causal effect. And this is known as instrumental variables estimation, where G, or our genotype, serves as an instrument for X or our exposure. And keeping in mind the key assumption that G affects Y only through X. And that's the assumption that basically gave rise to this equation here, and that gave rise to this ratio over here, or the expression for the causal effect beta X Y. So usually, we try to narrow it down to a single genetic variant to try to explain what's happening with the formula. So let's say we study the effect of LDL cholesterol or coronary heart disease. So if we have a single genetic variant or a single nucleotide polymorphism, its causal effect can be equal to 0.2. And the single nucleotide polymorphism will be coded as the number of effect alleles, G, let's say, in this case. So either 0, 1, or 2, depending whether the SNP was a homozygote or a heterozygote for either of the reference or the effect allele. And the same variant will be associated with disease risk by having this coefficient equal to 0.1. So how can we now estimate the causal effect having these two data? We can use the Wold estimator. So the Wold estimator is the name for the ratio that we introduced in the previous slide. So you basically take the beta GY divided by beta GX, and then you get 0.5. And it's the ratio of genetic associations that gives the causal effect in case. This is just an example, so don't take it for granted. So the interpretation here will be that if we increase LDL cholesterol by 1 unit, it will increase the disease risk by 0.5. So when we have one SNP, we have just one causal estimate. And the only data that we used was the beta GY and beta GX that come from genome-wide association analysis, usually for from one side LDL cholesterol levels, and on the other side coronary heart disease as a binary outcome being present or not. But the practice is not to do this on a single SNP, so we have to go from one SNP to many SNP, or as many as we can encompass. So we use multiple genetic variants as instruments, and each SNP will in that case provide its own ratio estimate. And these estimates will usually not be identical for the same exposure and the same outcome that we are investigating, because of the random variation in the data and because some SNPs are measured more precisely than others. So we have to keep this in mind. And we have to try to combine the effects across multiple SNPs into a simple or a single causal estimate for our Mendelian randomization analysis. So if we will have a SNP with a large sample size and a strong association with the exposure, it will typically give us a more precise estimate. And from the other side, if we have a SNP with a small sample size, will give less strong association, so we have to also take that into account. So we should not treat all SNPs estimates equally. So we should not treat all Wold estimates, all Wold ratio estimates equally, but we have to introduce some kind of weighting to this. So how can we combine these multiple SNP specific estimates while giving more weight to more precise ones? So we use something that's very common in epidemiology. We use inverse variance weighted method. So we want to estimate the causal effect of an exposure on an outcome using multiple genetic variants. We estimate it for each SNP, and then we introduce inverse variance weights, which basically say that you are inversing the variance. So here we have 1 over the standard error of our causal estimate for the SNP in question. And then we take these weights and we basically calculate the standard error using this formula here. You don't have to remember this. Usually the program does all of this for you. But you find the fixed FX estimate as this expression here. So our final causal estimate for the effect of our exposure to our outcome will be equal to this if we are using the fixed FX inverse variance weighted method. So it will be a sum of these weighted estimates for each SNP divided by the sum of the weights. And that's basically the fixed FX meta-analysis estimate, usually done when you do also meta-analysis of genome-wide association studies. But if we want to take in heterogeneity between these estimates, then we can use the random FX model, and then the weights are calculated in a bit different way. So it's not just 1 over the standard error. We add also this between study variance with tau squared, and then it also encompasses this heterogeneity between the estimates between the different SNPs. And that in that case, the random FX estimate will be actually the sum of these weighted estimates with the weights that come from this formula, also divided by the sum of weights for the random FX method. It's a bit more complicated, but again, depending on the results of the Cochrane's Q test, whether you have heterogeneity or not, you will decide to use either the fixed FX method or the random FX method for combining these causal estimates across multiple SNPs that are present in your analysis. So that's basically the math and the formulas behind the simplest method of performing Mendelian randomization analysis. Of course, there are multiple methods, but there's not enough time to go into the math behind all of them. But in practice, we would usually perform Mendelian randomization as a 2-sample Mendelian randomization. What does this mean? So you can either perform Mendelian randomization using publicly available GWAS summary statistics. So you would take GWAS for your exposure. For example, I had a paper on the effect of vitamin D on thyroid diseases. So I had to take GWAS summary statistics for vitamin D levels. And I also had to download the outcome GWAS being, let's say, Hashimoto's thyroiditis. And then I had to combine these two GWASs into a single working directory. I would do some further analysis in order to be able to use them in Mendelian randomization. You can also perform a 1-sample Mendelian randomization when you have individual level data for your both the phenotypes and genotypes, or you just have the GWAS results. And it can be performed in a single data set, but usually the practice is to perform it using 2 independent data sets. Of course, the important thing is to keep in mind that the GWASs have to be performed in people of similar ancestry. So if a GWAS for your exposure is performed for people with European ancestry, then it also has to be performed for the outcome. And it says here that the same SNPs are used as instruments in both data sets. Once you extract SNPs that are instruments for your exposure, you will go to your GWAS summary statistics for your outcome and extract these same SNPs that will later on go into the calculating the Wald ratio and calculating the fixed or random FX estimates from multiple SNPs. So in this case, no individual level data are required, and that's something that makes Mendelian randomization very popular, because you just need to have you have to have a server. You need to have some kind of let's say enough memory or capacity to perform these analyses depending on the size of the GWAS data sets. And then you can run all of the analysis locally using publicly available data and get your estimates of causal effects. That's why Mendelian randomization is so popular, and that's why we have a huge surge of Mendelian randomization papers in the last few years. So what's basically the workflow of an MR analysis if you want to perform one? So as I said before, you have to select a genetic variants associated with the exposure. So this will basically mean to get the GWAS results for your exposure and extract the SNPs that are significantly associated with your exposure, depending on the significance level that it is known in the field, or if you want to be more strict, you can also be more strict. Then you have to extract the SNP exposure and SNP outcome associations from GWAS. So these are the beta GX and beta GY that we mentioned before in the formula. And then you have to harmonize the data. So you have to ensure that the consistent effect alleles are across the dataset. What does this mean? So it has to mean that the beta GX is in relation to the same effect allele as beta GY is. So this gets complicated if you have SNPs where you cannot determine what allele is the effect allele, so for ambiguous SNPs. But this can be done pretty easily by some pre-built functions that can harmonize your data once you input the genome-wide association summary statistics into your code. And then you will compute the SNP-specific causal estimates, and you would combine them using methods such as inverse variance weighted, or whichever method you want to use. There's also weighted mean, weighted mode. You can also use all of the methods that are mentioned here today are frequentist methods. You can also use Bayesian methods. So you can also perform Mendelian randomization using Bayesian models that assume some kind of a prior distribution of these causal effects, and then it observes the data and then updates these priors into a posterior distribution. So the benefit of Bayesian methods is that you can use all of the SNPs that are present in a GWAS, whereas when you use frequentist methods, you can only use the SNPs that are significantly associated with exposure. So this basically limits the amount of variants that go into the analysis. The overall recommendation is to try to perform multiple kinds of analysis so that these can be viewed as sensitivity analysis, so that you don't have a false positive result that's stemming from just using a single method. So we're trying to confirm our results using various methods that have various assumptions. So if we see a causal significant effect in multiple methods, that can give more validity to our results. And analyses are usually performed using summary statistics, as I said before. As large as GWASs as you can get, the better. You will have more SNPs that are significantly associated with the exposure, and that will subsequently go into analysis. You can use public repositories for this. There's also a platform called MRBase, which can perform Mendelian randomization for you. So you don't have to do anything locally. You can click the analysis on the platform, and it will perform the analysis for your exposures and outcomes of interest. And you can also download dedicated software tools. For example, our package 2Sample-MR is something that I use in my analysis, and I think it's pretty simple to use. And it has a great documentation. You can visit their website, and they have a very, very practical guideline on each step of the Mendelian randomization, on the harmonization, on downloading data, on performing the model, and so on. So it's a very great tool, and it does automate the data extraction, the harmonization, and the causal estimation. You just have to specify the methods that you want to use, and then you can simply perform the analysis yourself with some kind of tweaks, of course, that if you want to make within your own analysis. So Mendelian randomization analysis can be implemented with relatively simple workflows, but the important thing is that we have to keep in mind the three assumptions of the Mendelian randomization that have to be in place, and we have to keep in mind also that we cannot perform Mendelian randomization just for any kind of combination of exposure and outcome. We have to have an exposure that is heritable, so that is influenced by the genome at least, in addition to some kind of other questions that are now arising with the rise of the Mendelian randomization papers that are maybe not methodologically valid. So there's not enough time to go into details about all of this, but I hope that within these 40 minutes, I have managed to go into the basics of the method. And if someone is interested in more, or what are the limitations, or what are the benefits of the analysis, and what you have to keep in mind when you perform one, you are, of course, always free to contact me through my email, and I'll be happy to help you with your analysis. Thank you for your attention.
Thank you so much for breaking down these complicated steps for me, who is not a mathematician, to a level that I can at least hope to follow to some extent. I cannot remember when was the last time I was, witnessing complicated mathematical equations explained in a nice way. So thank you so much for presenting this. We already have some of the questions from the audience, but before I would give myself an opportunity to ask some questions, and then while you are answering, I will interpret these questions for you. So, as you mentioned, in the last 10 years, we have really seen a lot of Mendelian randomization performed, probably due to the fact that we have a lot of genomics platforms that are performing in various diseases, first in cancer and then in other population studies and regarding different diseases. But as with any methodology, when you approach and try to explain it, it always looks so perfect. So I'm going on a thin ice here to ask, so what are the most obvious limitations in the application apart from those that you already mentioned? If we want to apply Mendelian randomization, you showed us the basic assumptions that we need to follow. So if you can back up this with a very clinically understandable example, that I would be very fond of that. And the third question is, we see that Mendelian randomization these days is mostly at least from what I'm following, is applied in a sense that the output that we are seeing is mostly related to the coding genes, because at least in UK Biobank you have the proteomics, you have metabolomics, and then you have the genomics, and then you can combine these things and see if some proteomic biomarkers are actually causal in a specific disease. But what if these SNPs, and we know that numerous SNPs are present in the regions of DNA that are non-coding, either non-coding RNAs or microRNAs, or if they are targeting the promoter regions, what would be our strategies then, and how we can overcome this? Okay, and that's what my side, and I will leave you to answer that, and then we can move on to questions.
Okay, thank you. So now, if I remember all the questions correctly, so yeah, I mentioned some of the assumptions, or the 3 assumptions that have to be satisfied. So the thing that we have to keep in mind is something that was published a few days ago by the founders of Mendelian randomization in PLOS Medicine, and it's gene environment equivalent. That's a new term that they made. So I was talking about the exposure as a modifiable risk factor, and the outcome as, let's say, disease, and the effect of the genetic variants on our outcome, and the change in our exposure that will be causally related to our outcome. So with Mendelian randomization, these changes that we expect that happen with the change in the exposure have to be, and that are influenced by the genetic variants, have to be equivalent to those changes that will be presented if there was a change in the environment. So this is something that's called gene environment equivalent. So we have to keep in mind the duration, the timing of these changes, the dose of these changes. So usually when you have changes that are consequence of genetic variants, their effects is lifelong. But in some cases, these changes, let's say in epidemiology or randomized control trials, this timing is limited. So there is a limited, I had the slide that shows the parallel of a randomized control trial and the Mendelian randomization. But here we also have to take into account the timing, the dose, the effect that is the consequence of the genetic variants and how long does it last and how long it will last if it was an environmental change that was changing this causal effect. So it's very well written in the short paper by the Professor George Davis Smith. So not to go into many details here, I can link it later on, or you can link it up. So it's called Gene Environment Equivalent, and it's a very important assumption for performing Mendelian randomization. Also, there's a nice YouTube video from Professor George Davis Smith, which says basically that there were instances of Mendelian randomization papers investigating the causal effect of noodle eating or on some kind of disease. Of course, this exposure, I don't know, I guess you can find GWASs that are performed for noodle eating, but there is no conceptual genetic basis to this exposure. So we also have to keep in mind that the exposure has to be linked to the genes, and this is something that we can test with the relevance assumption, and we can test with the specific statistical measures. Regarding the next section, you were talking about how can we decipher if something that's called pleiotropy. So in Mendelian randomization, we have to keep in mind of the horizontal pleiotropy, and we also have something that's vertical pleiotropy. So basically, the vertical pleiotropy is the causal effect that we are estimating with the Mendelian randomization. But the horizontal pleiotropy, or the variants in the genome influencing both our exposure and our outcome, be it through separate mechanisms or through a shared heritable mechanism, is something that can confound our results and that we have to keep in mind. So the mitigation for this is that in my papers, I use the Bayesian approach. So I use the Bayesian method that's called CAUSE, C-A-U-S-E, which basically models all of the SNPs in the genome, and it puts a prior assumption, and it tries to decipher whether the causal effect, whether the effect observed between the exposure and outcome is truly the consequence of the causal effect, or is it the consequence of a shared heritable factor that is making both our exposure and outcome seem correlated. So that's something that can be used, for example, as a mitigation method. And if there's anything that I've skipped,
the third one was related to the fact that now mostly we are focusing on the coding regions, but what if the SNPs are in either long non-coding RNA regions or microRNA regions or promoters? How we approach the Mendelian randomization.
But in my paper, I did not focus on coding regions. So it's a question of whether you would more frequently see SNPs in coding regions be more statistically significantly associated with the exposure. But there is basically, for the method, there is no limitation. So you can use also SNPs that are within the introns or whatever, if they are significantly associated with your exposure.
Okay, perfect. So we can start with the questions. We have two questions from the same person. Ivank, I hope I read it correctly. He says, many thanks for the great presentation. I have a question. In genome, there can be 20,000 known genes. So it means there would be thousands of hypothesis testing in causal modeling to inform causation. Is it common to control for multiple testing like FDR or similar methods? So that's the first question, and then we can move to the second one when you answer.
That's a great question. So as you all may know, in genome-wide association analysis, we are using the Bonferroni correction. So we are basically dividing the 0.05 significance level with 1 million, because we assume that we have 1 million independent SNPs in the genome. And that's a threshold that comes to 5 times 10 to the minus 8. And now for the Mendelian randomization, it depends on the number of SNPs that go into the analysis. So basically, it will be recommended to control for the false discovery rate. Either by using Benjamini-Hochberg method or whichever method that, wherever you are doing multiple testing, it's very recommended to use this kind of correction.
Perfect. The next question from the same person: how can causal modeling, including 1,000 public GWAS datasets, be linked to transcriptome global gene expression data? I mean, what would be feasible way to integrate two omic layers, genomics SNPs and transcriptome mRNA levels, with the purpose of explaining the observed phenotype? In the context, do you also work on EQTLs? Another thing that is very popular these days.
That's a great question, but I think here we have to keep in mind that the genetic variants here are just used as instrumental variables. So basically, we are just exploring the causal effect between two phenotypes, so the exposure and the outcome, and we are just using the genetic variants as instrumental variables so that we can construct the instrumental variable method. In that way, we are just using the relationship between the genome and the exposure and the genome and the outcome to model the analysis. I'm not really sure how can we use transcriptomics and EQTLs. Maybe, don't take me for a word, maybe someone has integrated this into Mendelian randomization analysis. It does make sense, but I don't know about it, so maybe we could check the literature.
I can comment on this. Again, not an expert at all, but I just want to comment that, for example, for interleukin-6, there has been some doubt about the role of inflammation in cardiovascular disease, because none of the inflammatory genes show super high GWAS statistics, you know, like a causality. And then what they did, they integrated the EQTLs with the GWAS and found that, for example, for, I think it was either interleukin-6 or interleukin-1 receptor, don't take my word for it, you can Google it. It was published maybe a few months ago. They show that in this scenario, when you are actually focusing on the relationship between SNPs and the transcript levels, it is much easier to find these relations. And I was trying to investigate how this works. What I found out is that you actually need, just to give a very theoretical answer to the question, but what I found out is that you basically need, in the same scenario, a few hundred samples where you run the genomics and transcriptomics to have capacity to integrate those two together, and then you will be able to extrapolate these conclusions in a validation cohorts. But you need to have the data sets where you have at the same time both levels of information. And I think there are some levels that are already out there, but not for all the diseases, probably just for cancer. Paolo, would you like to ask something in this regard?
First of all, thank you very much, because this was a very nice, very clear presentation, very useful for all of us. Thank you, Nikolina. Now, I have a question which is maybe it's a naive question, but if you take, let's say, if you do Mendelian randomization from according to the age, okay, clearly 5 or to 10 years of age compared to 70 to 80. Of course, the exposome may have done so many things. So, do you have less confounders probably at earlier age, but less outcomes? So how can you manage the age? Is there a concept, some consideration on the age of the cohort that you are taking into consideration for Mendelian randomization?
For Mendelian randomization, in this basic sense, no. But and also for randomized controlled trials, randomization method would rarely rely on age-related randomization, because you have to have the equal probability for each participant to either be included in the exposure or the control group. So it will be a little bit tricky to randomize them according to age. But we all know that as age increases in participants, all of the, let's say, age-related diseases or parameters are exacerbated. So within Mendelian randomization, age in the basic sense is not included as a confounder, but it can be, there is a method and we can include, let's say, known confounders into Mendelian randomization. That will be a little bit more complex modeling, but it can be done. Relating to age, I don't have a definite answer for that because age is pretty complex, but maybe some kind of other known confounders that are known can be also included in the modeling, and then we can clearly exclude their effect so that it does not confound the causal estimate that we are trying to compute.
Thank you so much. And clearly, of course, the family history put on top of Mendelian randomization is a potent increase, is increasing the power of the overall analysis. But there's a problem how to collect family history, which is a major problem everywhere, because it can be very imprecise. So I think this is another point that to have not to have the full picture.
Thank you, Paolo. We have another question from Carolina in a chat. She says, I really like the context of the need for the exposure to be heritable. For me, is quite controversial the amount of MR literature using microbiome exposure when heritability is so low. So do you have any comments on this interplay between microbiome and Mendelian randomization?
That's a great question. I'm not trying to point out the microbiome, but in each Mendelian randomization analysis, we have to give statistics on how much the exposure is being related to the genetic variance. And this is something that we can calculate by the so-called F statistics. And basically, we are calculating the amount of variance within the exposure that is explained by the SNPs that we have in the data set that's present to us. This may also be known to you if you are performing GWASs as SNP-based heritability or narrow-sized heritability. So basically the number is put on the heritability estimate of the exposure. And the higher this number, the more reliable the Mendelian randomization analysis is. And that's something that also has to be reported in a Mendelian randomization paper that is quality done, but it's not usually always the case.
Okay, cool. Thank you. Let me check if we don't have any other questions. Anybody else want to ask? Feel free to join in discussion. You can also use microphone. Just raise your hand, and then I will provide you I will allow you to join in. So is anybody else interested in participating in the discussion? Do we have any other questions? Let me just check the attendees list if anybody has raised hand. No, not so far. Okay, so cool. Perfect. Well, then we can conclude for today. I really thank you so much for this presentation and for willingness to interact with us. I think this is one of the many things that is going to happen between the ending AtheroNET and beginning Inflammomix cost actions. And I wish you, everybody, a nice weekend. Enjoy, especially if you're near seaside. Probably it's much better than being here, but yeah, we cannot all live near the seaside, right? So, thank you once more, and good luck with the project. I'm really happy to see the progress on the thyroid gland story, and see you soon, I guess. Goodbye, everybody. Keep in touch.
Thank you.
Bye bye. Thank you so much.